Hi and welcome back to another video podcast from podcastschool.net. Today we're going to be taking a look at the transistor. The transistor is a semiconductor device commonly used to amplify or switch electronic signals. Now, that's the definition, and very easy for me to say, but what does it actually mean? Well, first of all, a semiconductor device is a device that conducts sometimes, depending upon external factors. So, whereas a piece of, say, copper or aluminium might conduct all of the time, and a piece of plastic would conduct none of the time, it would be an insulator. A semiconductor is somewhere in between. I said it'll conduct depending upon something, external factors. Okay, so that's pretty much what that means. I've said there that the transistor is a fundamental building block of computers, and I think I've said that to you before in the last podcast. It's like what cells are to humans. Some transistors are packaged individually, but most are found in integrated circuits. Okay, let's sort of put that, integrated circuits. So you've probably seen discrete transistors, and by discrete I mean transistors that are that are just one of them contained in a can. It's important that you realize at this point that transistors you can put them into an integrated circuit, thousands and thousands and thousands, and that's what's inside your processors and inside computers, and that's basically what builds up all the electronics we use today. Okay. Fundamentally then, I've said that the transistor acts like an electronic switch, and if electrical voltage is passed through the base leg, alright, let's first of all have a look at what we mean. The transistor looks like this. One of these is the base leg. Then the transistor is switched on, and the electricity can flow from the collector to the emitter. Okay, so we've got three terms there: the base, the collector, and the emitter. So depending on what way we're looking at this, one of these could be the base, one of these could be the collector, and one of these could be the emitter. And I'm going to show you how to recognize each one of those right now. There we go. If you look at this from underneath, then well, first of all, look, there's a little tab here. You see that on the can? So that's how you recognize that. And then if you turn it upside down, so if it's showing there, this is the underside view. If you turn it upside down, the emitter, which is what I've signified by the E, it's just to the left of the tab. And then if you go clockwise, then you get base and then collector. That's clockwise, isn't it? Yeah, that's clockwise. Okay, so emitter, base, collector. And I'll tell you what those mean and what those legs are for in just a second. Alright, but first of all, let me just give you a little bit of history. I've said that the development of the transistor in the mid-1950s was the beginning of the electronic age, which is kind of weird when you think about it, that we've really only had modern electronics for the last, well, coming up now in 60 years. It seems very new. Well, it is very new. This is a photograph actually of the first working transistor. It's actually a replica. So you can see that it's quite big, and it's just obviously a prototype. But that was the beginning of the transistor as we know it. And I've said there that this device can be made very small. Many thousands can be made on a single piece of silicon, 1 millimeter square. And if you have a look, this is just an integrated circuit. It's a mini DIL, or a DIL meaning dual in line, and that refers to the legs here that we see. See these legs along one side, and we can't see this side, but down the other. Okay, and they're in line, so we say dual in line. So this is often referred to as a DIL. But in any case, the reason for its size is not because this grey area is packed. It's not because there's loads of stuff in here. It's not that at all. It's the fact that we can really only solder as humans to larger things. So they're made to a certain size or a certain pitch. The actual working of the transistor is just contained in this tiny little bit here, which you can just see. And if you look very carefully, but you may not see it, it may not come out so well in the podcast, there's little metallic lines running off this, okay, and they're running out to the legs of the IC, okay. So don't be fooled into thinking that this is packed. It's not. It's not at all. Okay, so let's have another look at this. So we said that we've got emitter, base, collector clockwise from the tab if you look at the underside view. Now, this is the symbol for a transistor, and I've already labelled that as the base. Okay, if you just bear with me for a second, I'll show you this all through, and then it might make more sense. So the base, this leg's called the base. The base switches the transistor on when a positive voltage is applied to it, 0.6 volts. And that's quite important, that 0.6 volts. So remember that one, 0.6 volts. So that's like, okay, so I tell my students that if you were to look at a switch on a wall, say a light switch, and you push the switch with your finger, the base is a bit like your finger. It's the one that pushes the transistor. It's the one that makes it work, makes it switch on. The collector, on the other hand, it collects the current from above. So if you imagine there's current up here available in this area, so maybe a line coming here, and it's able to flow into this direction of the transistor, then it collects the current. And then the emitter emits the current. Now, might not be so clear. If that's the first time you've seen it, or I've heard that explained, that might seem a bit like gobbledygook, but I'll put it in context in a second and you'll see what I mean. Now, the current flowing into the base of the transistor is much smaller than the current flowing from the collector to the emitter. Okay, so I've said already that current flowing in here switches the transistor on, so current in there switches it on. If there's a current source available up here, then it is able to flow down through the transistor and back out again. Okay, it's able to do that only when there's current flowing into the base of the transistor, or actually more accurately, whenever there's a high voltage at the base of the transistor, which would be about, as I said, 0.6 volts. So a higher than 0.6 volts on the base makes this switch on. Okay. So a large current can be drawn through the collector to the emitter, whereas a small current is really only what's needed at the base. I'll just read this through. The voltage of the base is normally fed through the current limiting resistor. Okay, so there'll be a resistor in here, which restricts the amount of current reaching the transistor. Too much current would destroy the transistor. The transistor only requires a voltage, I've said that before, of 0.6 volts to turn it on. This is known as the threshold voltage. That's important. And this 0.6 comes up time and time and time again. Now we've jumped right into an application here, and you can see that the transistors in the circuit, and well, with various other things. Now, depending on whether you've seen this stuff before, this will either be easy or maybe a bit more difficult, but I'll explain this through just now. We have a battery, and of course the battery is providing the energy to the circuit. There's the plus side here, and you always know the plus because, I'll just draw it over here, a plus, the battery symbol looks like that, and it takes more lines to make a plus than it does to make a minus, so you'll never forget that the long side is a plus because it takes more lines to make a plus. Okay, so that's the battery. So this top line will all be at whatever, 9 volts if it's a 9 volt battery, and the bottom half of the circuit will all be at 0 volts if that's the way we connect it in to the battery. Okay, and we have done here. Now, we've got a transistor, we've recognized that. Let's look at these. This is a resistor, and you should recognize that, and another resistor here. Down below we've got an LDR, and an LDR is a light dependent resistor. In other words, it's just another resistor, but its resistance changes depending upon the amount of light falling on it. And you'll have heard me say before that an LDR has a big resistance in the dark. And just for the record, there's something called a thermistor, and it has a big resistance in the cold. And I always say, if you remember the 3 words, big, dark, cold, you remember how both of those components operate. Big, dark, cold. So for the LDR, it's a big resistance in the dark, and for a thermistor, it's a big resistance in the cold. Big, dark, cold. Okay, so here we have a resistor and another type of resistor. This bit is, you might recognize, a what is it? Forgot myself for a second. It's a potential divider. So this is a potential divider, and that's the input portion to the circuit. I guess this bit is the process portion of the circuit, and then this bit is the output, or the LEDs. Okay, and they're going to come on. So how does this work? Well, let's have a look. Okay, so in the dark, well, so let's say in the light first. So in light conditions, the LDR has a small resistance, and you know that voltage splits in the same proportion as the resistance. Okay, and there's an equation for that as well, which you can look back and find. But just generally, voltage splits between here and here depending upon the resistance. Because if you think about it, if this up here is at 9 volts and down here we have 0 volts, never mind this for a second, somewhere in between we got to get from 9 and back down to 0. So here, this point must be somewhere in between. But what is it? It depends upon this component and what this is doing. Okay. So in light conditions, this is small resistance. Voltage splits here in accordance with the resistance, so this will have a smaller portion. So you can say that the voltage at this point will be quite low in light conditions. But then, when it gets dark, the voltage here will, across this component, will increase. Okay, so instead of this maybe being, I don't know, like 0.1 volts, it'll start to increase up and up and up. Okay, there'll be a slight voltage drop across the resistor, but not much. In other words, the voltage here at the base of the transistor is going to go up as this goes up, and you know that this goes up as the darkness increases. The light level, darkness increases, light level decreases. Okay, now you know that the transistor switches on at a voltage of 0.6 volts, the threshold voltage. When that happens, current can flow from the collector through to the emitter. And if current can flow, it means that it can find its way from the positive side right round, down, importantly through the LEDs of course, down and out to 0 volts, and of course back to the battery. In other words, a complete circuit. So the current will be happy to do that, and it just so happens that while it has to do that, it has to go through the LEDs. Let's clear the screen, it's getting a bit messy. The LEDs, and of course make it light. In other words, to cut a long story short, when it gets dark, the resistance here increases, the voltage here increases, and the LEDs turn on. Okay. Now, lastly, we have seen that current flowing into the base of a transistor will turn on a larger collector current. It's known as current amplification. The ratio of collector current to the base current is a measure of the amplification, which we call the transistor's gain. The symbol for the transistor current gain is HFE there, or beta. So a small current flowing into the base of the transistor, it might only be 250 microamps, let's say, can switch a large current of maybe 50 milliamps into the collector. So the HFE works out as 0.05 divided by 0.00025, and that's just a matter of getting your millis and your micros right. And the current gain therefore is HFE. Is 200. Is HFE, but it's also 200, and that's what we need. That's what we might need to find in an exam, for example. Okay, I think this is last then. The power of a transistor is related to the size of the collector current that can pass through the transistor before it's damaged. The current varies from a few milliamps to many amps. And this table lets you see how each type of transistor varies. Okay, so this is types of transistor, all just a little bunch of codes and not very exciting. But take it from me, they're just names of different types of transistors. You've got gain here as well, and you've also got IC max. That's the collector current max, and that gives us an indication of the power which it can withstand. All right, now that's basically the transistor. Next podcast we'll have a look at how we might build upon this table in order to get the best of both worlds from two transistors. That's called the Darlington pair. So that'll be the next podcast. But for now, if you have any questions, of course, don't forget you can email me. It's info@podcastschool.net. I try to keep these podcasts as quick and as short as I can, so that A, you don't get bored, B, I don't faint with effort. The other thing is I try and keep them under 10 minutes. This one's going on to be 13 minutes, so I'll finish now. But don't forget, pick up the notes and email me if you have any questions. Okay, until next time then, bye-bye.